from Group 5, Session 2, we present soil properties of absorption between clay and soil. We talk about introduction. First of all, what is soil? Soil is a mixture of inorganic and organic components present on the Earth's surface. Fine rock particles of varying size make up soil. These are from sedimentary and weathered igneous rock. After wind, rain, heat, cold, and other natural variables have acted on the rock particle. For the soil, absorption is a method of treating and disposing of effluent from a treatment unit by absorbing it into the soil. For water absorption in sand, select a sandy soil with very small pebbles that is good for aeration but not for water retention. Clay soil, on the other hand, have colloidal particles that can store water but have limited aeration. So, for the objective in this research, the objective of this project is to differentiate water absorption between sand and clay using permeability tests. For the aim of this research is to explain the procedure of falling head and constant head test.
Literature review. AMR F. Al-Hakim 2016 wrote that there are a few methods that can be used to measure the permeability of soils. Permeability can be measured by using field falling head permeability and full-scale pumping test. The falling head is used to measure the permeability at specific depth, while the pumping test provides an average permeability for the soil stratum. Second, based on Mavis and Wild CEF 1936, the porosity of a granular material depends on the gradation and shape of the grains and on the compaction of the sample. Regardless of the grain size, uniform sands with geometrically identical grains forms compacted in the same way have roughly the same porosity. The difficulty in determining the relation between permeability and porosity lies in obtaining a reasonable wide range of constant porosities with the soil of a given size and shape. Last, Lemty, 1955, concluded one of a soil's most fundamental and crucial characteristic is its permeability. It factors into almost all seepage, settlement, and stability issues that the soil engineer must deal with. The permeability soils are frequently referred to impervious and do not undergo permeability testing. The importance of a soil permeability less than 1 year per second is growing for soil technology for both practical and theoretical reasons.
There are two experiments that are required to determine some properties of absorption between sand and clay, which are the constant head permeability test and the falling head permeability test. The constant head permeability test is to determine the permeability of sand, while the falling head permeability test is to determine the permeability of soil of intermediate and low permeability clays. First, for the constant head permeability test, the following procedure is required to determine the permeability of sand. First, we need to prepare permeameter cells. We need to measure the mean internal diameter, the distance between the center of each set of manometer connection point along the axis of the cell. Then, we calculate the area of cross-section of the sample and the approximate mass of soil. To create a permeameter cell, the material must first be reduced using the standard riffling procedure. Dry the soil by letting it air dry before taking the test sample. The sample will be placed in the cell by one of three methods, which is compacting the eroding, dry pouring, and pouring through water. On top of the soil, place a second porous disc, a wire gauze disc, and then a layer of glass wall or gravel filter material that is about 40 mm thick. Push the piston downward until the perforated plate is in contact with the filter material. Hold it down while tightening the piston locking collar. Next, connect up. Use piston, plastic or thick wall rubber tubing to connect the top output of the cell to the vacuum that is equipped with a water trap. Close the input cork after connecting the cell's base nozzle to the air water supply. Saturated the air and link up tests are performed after that. Turn on the constant head device water supply, which should first be turned on at a low level. Empty the measuring cylinder before beginning a test run. Then set the timer to begin when the cylinder is positioned beneath the outlet overflow. Read the water levels in the manometer tubes and gauge the output reservoir water temperature. Repeat the test, empty the cylinder, and perform 4 to 6 more runs at intervals of roughly 5 minutes. Note the moment the first run begins on the clock. For the falling head permeability test, the following procedure is needed to achieve the objective of this experiment, which is to determine the permeability of soil of intermediate and low permeability clays. The apparatus must be set up. A constant supply of the air water is not required because the amount of the water moving through a sample with low permeability is fairly little, but the reservoir supplying the deairing tank should be replenished with distilled or deionized water. Next, calibrate the manometer tubes. The 3 manometer tube's cross-sectional area should be calculated for each tube as follows. First, add water to the tube until it reaches a known mark that is located close to the top of the scale, until the level in the tube has dropped by at least 500 mm. Run off water from the tube into a weight beaker. To the close millimeter, read the new water level on the scale. Weight the water-filled beaker that came out of the tube. It is possible to determine the manometer diameter for each tube. Repeat the measurement 2 or 3 times, then average the finding. Prepare a sample. A core cutter can be used to take an undisturbed sample. Confirm that the sample fits properly inside the body and that the sample perimeter is free of any holes that would allow water to enter. Build the cell. Connect the cell, the air, the sample after saturation. Fill manometer system. Run the test. Open the screw clip at the inlet to let the water run through the sample and down into the standpipe, then check the water level there. Start the timer clock as soon as it reaches the desired level. Stand the time clock as soon as it reaches the desired level. Watch the level as it rises. Note the time it reaches and then stop the timer. Close the intake screw clip. Repeat the test.
For result and discussion, through filling empty areas, water moves through the soil. Water flows along a curving course rather than in a straight line. However, flow is thought to be in a straight line at an effective velocity in soil mechanics. The size of the holes affects the flow rate. On the principle of Darcy's law, it is determined that due to their depth of penetration, microscopic voids significantly enhance the sample's permeability. Sandy soils are noted for having high permeability, which leads to high infiltration rates and good drainage. Small pore spaces in soils with a clay texture allow water to percolate through the soil more slowly. Because of their limited permeability, clay soils are known to have low infiltration rates and poor drainage. In the context of water absorption, clay soil absorbs more water than sand because there are more crevices between clay particles, so there is a lot of available surface area for water molecules to cling to. Due to its enormous surface area, clay has the highest capacity of a mineral components in the soil to absorb water. Permeability is also influenced by other elements including hydraulic gradient, soil type, texture, and particle size distribution. The importances of permeability are: a saturated soil's rate of settling under load is influenced by permeability. The permeability involved has a significant impact on the stability of slopes and retaining structures. The permeability of the soil utilized heavily influences the construction of earth dams. And lastly, the permeability of soils is used to create filters constructed on them.
As a conclusion, the water absorption between sand and clay can be differentiated using permeability methods. According to the findings, clay absorbs more water than sand. It's because clay soil can store a lot of water. Clay soil particles have larger space between them, which increase their potential for retention. These soils are better at absorbing water due to its thin pore size and small diameter. Clay soil is very water soluble. Sand and clay also have the benefit of being used in building. Sand is frequently used in construction, for instance, where it gives other material like asphalt, concrete, mortar, render, cement, and scrape, but strength and stability. However, it's offered thermal good and reasonable effective thermal insulation. In composite material, including adobe, cork, ram, earths, metal and dope, clay pastel, clay mortar, ceramic, and others. Clay is a critical component. Clay has a good robustness, stability, and durability. Lastly, clay has a better water absorption